So here are TFR astronomy cameras at various Indian telescopes, past and present. And here you can see Telecam 1 and 2 cameras at Mount Abu Infrared Observatory. Here Telecam 2 is at Ayoka Giravali Observatory. And currently Telecam 2 is at Devastal Optical Telescope. It has been operated from main port, and currently now it is at the side port of the TOT. Here is a Tirspec camera which is at Himalayan Chandra Telescope, and Tanspec camera which is at Devastal Optical Telescope. Now I will discuss the infrared detectors. So here you can see few infrared detectors. These are ITAR, basically military devices, and thus they come under ITAR certification, and these are very expensive devices. So here I have shown three devices, four devices actually. So the first one is a indium antimony detector called Aladdin. This is 512 by 512 pixel detector. It is used with Telecam camera. This is mercury cadmium telluride detector called Hawaii 1. It is 1K by 1K pixel detector and is used in Tirspec camera. So here I have shown one detector, but basically there are two versions. So mercury cadmium detector, H1RG and H2RG. So H1RG is 1K by 1K pixel and H2RG is 2K by 2K pixel. So this has been used in Tanspec camera and also targeted for IRC's project. So here is an infrared detector architecture. It is a two-layer device, and top layer is a detector array where illumination falls, and bottom layer is a silicon readout array. These two layers are connected with a indium interconnect, which provide electrical contact as well as a thermal path. Then output is taken in a multiplex type of output. And here you can see the pixel architecture at the left and schematic at the right. So on top you can see the photodiode in the substrate, and bottom you can see the silicon readout multiplexer, and these are connected with the indium pump. So here I have shown a pixel schematic. So here is a photodiode in the substrate, and here is the indium pump. The signal from the photodiode is given to a source follower. This is a pixel source follower, and after that it is coupled to a vertical read bus. So you can see different clocks and biases over here. VB1, VB2 are biases, and this is a reset switch clock, and this is read control clock. So basically reset, when you close the reset switch, a VB1 gets applied to the photodiode, and the photodiode is reverse bias, and you basically clear all the electrons collected from the photodiode. And here is a detector output schematic. So signal from the vertical read bus is eventually coupled to a horizontal read bus, and you can pick that output raw from that output end by using this switch over here, and otherwise you can use a output source follower and take a buffered output at this output. So here is a basic infrared detector controller schematic. So here is a detector or FPA, focal plane array, in the camera. So the camera will have filters, lens system also, and of course the cooling system which will cool the detector. So here this is the detector controller, and this detector will require power and bias voltages, clocks, and will get the video or output from the detector. And here detector controller will have blocks like microcontroller, processor, DSP or FPGA, memory, communication block, A to D converters, D to A converters, switches, drivers, etc. So when we require one, we'll first require a power and bias to be applied to the detector. So we'll first program these DACs over here, and through suitable drivers we'll apply power and bias voltages to the detector. After that, clocking is required. The clock levels will be generated by DACs over here, and switching will be done by these switches. And after suitable drivers, we will apply this clock to the detector. The video output from the detector, after suitable analog processing, will be applied to a to D converters, and then the digitized data can be stored to a memory, and it can be communicated to the computer. So these are the typical clock waveform required for the detector. So this could be a initialization clocks, which basically put some certain values into register inside a detector. The top one readout clock. Then detector is read out into two formats basically. So one is a reset expose sample. First you reset the photodiode, you allow the photodiode to collect the light, and after certain exposure time you sample that pixel. The other way is the up the RAM sample. So here first you reset the detector, and while the detector is collecting the light, you have multiple sampling done on that signal. Now I will present Telecam camera. So this is a TFR near infrared imaging camera, Telecam 2. So here you can see the photograph. This is the window through which light enters into the camera, and this is a cryocooler on top of this camera. So these are the specification of this camera. This is currently at DOT Aries Uttarakhand. And this is the largest optical telescope in India, 3.6 meter. The wavelength coverage is about 1 to 3.7 micron. The detector is LN3. The cooling is done by the cryocooler. And this camera is currently at DOT 3.6 meter, and it is available for observation worldwide through peer-reviewed proposal system. So this is the only camera in India which operates beyond 2.5 micron with ability to observe a power band, that is polycyclic aromatic hydrocarbons. Then this is on the side port of the TOT. So that allows a near simultaneous NIR observation along with the main port instrument. And being on the side port, it is continuously on. It allows us for operate for longer times, as the main port or instruments are basically used for with the time shared basis. Here is a Telecam observational setup, and here is a Telecam camera. This is the telescope part. So Telecam camera, this is the cold head of the camera, this is the compressor of the camera, and these are the electronics of the camera. So light from the telescope enters through this window and focused onto the detector through this lens system and filters. Then we have a temperature controller over here, which maintains the detector at 35 Kelvin, the filter selector which select the filters, and the FPA controller which basically reads the detector and stores the digitized data in the computer. This computer is controlled by an observer console at control room. This is a Telecam software GUI which supports full frame and sub-array modes. So here is one sample image of the captured image. Uh, we have done an upgrade of Telecam from 1 to 2. So initially Telecam 1, this is the Telecam 1 camera, had a detector of 58 by 62 pixel. Then we upgraded it to Telecam 2. Now it uses 512 by 512 pixel. And we have developed in-house the fan-out board which operates at 35 Kelvin. And we have also modified the optics within the camera. So this is the Zmax latest of this Telecam 2 optics. So here are few results from this Telecam camera. So this is a star forming region. Then there are few galaxies over here. Then these are the clusters. These are the planets, and here is a data from a Pluto occultation for atmospheric study. Now I will present transfer camera. So this is the transfer camera over here, and these are the specifications. Now this transfer camera is currently at DO2 Aries Uttarakhand. Its wavelength coverage is 0.55 to 2.5 micron. So spectral resolving power in a cross dispersion mode is about 2750, and in prism mode it is 150 to 400. So it has a reflective slit which allows us for a guiding mode of the camera. Then it uses two detectors, H2RG and H1RG, and it uses a hybrid cooling. So liquid nitrogen for cooling detectors and optics, and cryocooler for cooling radiation shield. This is a collaborative project between TIABR, Aries Uttarakhand, and MKR USA. So Telecam Transfac basically has two cameras which allow simultaneous imaging guiding and spectroscopy, and has a wide coverage from optical to near infrared, so 0.5 micron to 2.5 micron. And this is also available worldwide through peer-reviewed proposal system. So this is the transfer camera at DOT telescope. It was installed in 2019, and these are some installation snaps where transfer is being carried to the telescope floor. This is the transfer compressor and gas pipe routing, etc. So here is a 10 spec optics. This is the inside of the 10 spec camera, and here is a 10 spec optics ray trace done in Zemax, and here is a 10 spec optics ray path. So this is the window through which light enters, and the F9 beam is converted to F12 beam and falls on the slits. These are reflective slits. So you can see slits over here and here. And then the slits is, this is the H1RG camera over here and here. So this acts as a slit viewer as well as imager and guider. So while H1RG camera acts as an imager, here is a filter wheel for that camera. Then after that, light from the slit is collimated on the grating and cross dispersion prism, and spectrum is imaged on the H2RG camera. So this part over here is a H2RG camera, as you can see over here. So here are some preliminary test and results from this camera. So here you can see the wide coverage of spectrum from 0.55 to 0.5. So these two are basically calibration lamp spectrum, argon neon and argon spectra, and this one is a continuum lamp spectra. And these two shows the a star spectra, and these are some extracted orders of those stars. And in the imaging mode, this is the imaging mode H1RG camera image. Here a cluster image is shown. So this has a successful simultaneous optical and near infrared wavelength coverage from 0.55 to 2.5 micron and deep imaging sensitivity with the imager. Now I'll present Ircs camera. So this is TIR near infrared spectrometer. So this is the camera, and the specifications are like this. It is current and cooling is done with the liquid nitrogen cooled. And this camera is also available for worldwide observation through peer-reviewed proposal system. The observations are done remotely from Crest Oscate with dedicated satellite link from ISRO. This is because favorable user conditions are at then being at Henley. And this way on the side ports also allows near simultaneous NIR observation along with main and side port, other main and side port instruments. So this is a telescope at HCD telescope, side port of the HCD, and this is the IO observatory, which is at height of 5500 meters. And in winters, the temperature plummets below minus 20 degrees centigrade. So here is a telescope optics. It has two modes. You can select between imaging mode or a spectroscopy mode. So here is a window through which light enters, and we have a slit wheels over here, which will be here somewhere. This is a three-fold design. So you can see fold 1, fold 2, and fold 3. And this is the collimator optics, and here are the camera optics, and filters are located over here, which you can see over this filter wheel over here. And in the spectroscopy mode, we'll use a GRISM and auto sorter. Those again will be in these wheels. So this is a compact three-fold design for a given envelope available at the HCT side port. So these are few results from the test spec. This is a star forming region, outward sources, supernova, and these are some spectra from few sources. I'll discuss IR payload for small satellite program, IRCs. So this is an infrared spectroscopic imaging survey, IRCs, satellite payload. So it is a satellite platform. Telescope size is about 30 centimeter. Field of view is about 14 by 14 arc minute. It will have two channels, so short wave 1.7 to 3.4 micron and long wave 3.2 to 6.5 micron. Resolution is about 100. It will use two H1RG detectors. So we have submitted a lab model, IRCs lab model. Final report is submitted to ISRO. So here is the IRCs block diagram. So we have a passive cooling shroud over here, and inside that we'll have a telescope, fiber fed two channel spectrometer, and two focal plane arrays. And this will be driven by a focal plane controllers. And this is the electronics module, which will interface with the focal plane controller. Then here is a lab spectroscope test setup. So here is a light source over here, and this part over here is a focal plane and slit plane fiber plates coupled with the optic fibers. And these two over here holds collimator and grating. And this is a liquid nitrogen cooled camera which houses the camera optics and the detector, S2RG detector. And this S2RG detector is read out by commercial sidecar ASIC.
1 more minute, sir.
Yeah. And this is a comparative spectra of this. And here is a we will be using an in-house developed controller. So here is a prototype S2RG controller we have developed, which is a microcontroller based, which interfaces with S2RG ROIC. And here is a image capture by this prototype, and here is image capture by this sidecar ASIC. This is the prototype. And here are few future directions. So future programs will develop a S2RG controller. We'll also upgrade our Telecam to data acquisition system. The tester camera is also detector upgrade is planned. Then of course Ircs engineering and flight model after the PDR. And another project, MOIS project, which is a multi-object, multi-slit spectrometer, where some work is Schematic modeling and controllers, slit mechanism controller, etc. work is going on. This is our team. Thank you.
Thank you very much for your detailed presentation on all the telescopes, telescope activities being carried out by TAFR, and one of the very largest telescope in Devastal also. That information you have provided, and some of the for future payload activities to ISRO also you have submitted the proposals. Very nice, sir. So with this, if any questions are there from the users or participants, we can take. And co-chair sir, Rana sir, if you have any questions, you can ask.
Just one small thing that I would like to ask. For this detectors, this 1K by 1K or 2K by 2K pixels, have you able to like calibrate them pixel by pixel? Or what I mean to say that, let's say, if some pixel becomes noisy or something, can you kind of disable, or what's the noise?
Hello, can you hear me?
Yes, yes.
Yeah, so basically we have to create a mask for that bad pixel, and then we'll have to filter out that using the mask.
Okay, but overall noise is kind of known for the entire detector, right?
Yes, yes, yes.
Okay, okay,
yeah.
Thanks.
Any questions from attendees? So, if not, we thank you very much, sir, for your detailed presentation. So
yeah,
we'll
thank you very much.
Yeah, we'll move on to the next presentation from Athira on geometric phase polarimeter.
Shall I start sharing my screen?
Yeah, 1 minute, sir. Yeah, now we can share your screen.
Okay. So good evening, everyone. So I'll be talking about a new concept, proof of concept, a geometric phase polarimeter, which is a lab model which we developed in CESI and Pionap lab at ISO Kolkata. So with this, let's get started with the presentation. Traditionally, how polarization is measured by a combination of pair of retarder and polarizer. You project to different polarization bases, and by rotating it or by introducing voltages to such as to the liquid crystal variable retarders, you do some algebraic summation or subtraction and create the Stokes vector, which generalizes the polarization parameters as IQUV. Now here, this method is not suitable for a high dynamical system, where because it requires a multiple measurement system, and for high dynamical system where the process varies from 10 seconds to 10,000 seconds, such as the coronal mass ejections from solar corona, or the other activities which are very high dynamic, this traditional polarimetric system is not suitable. So we were hunting for an alternative system which is a sort of a single shot measurement, and we came up with the geometric phase polarimeter. So before moving to the polarimetric system that we developed, I would like to introduce some basic concept on geometric phase, what it is, and let's go to the basics. So we know that light contains angular momentum, and there are three types of angular momentum: spin angular momentum, orbital angular momentum, which is again divided to intrinsic and extrinsic part. Spin angular momentum is the fourth Stokes parameter, which is Stokes V, which is related to the circular polarization or the elliptical polarization state. So it can be, the values can be from -1 to 1. Whereas in intrinsic orbital angular momentum, it is related to the phase front structure, and it is related to the topological charge of the wavefront, and it can vary from -infinity to +infinity. Now, extrinsic orbital angular momentum happens because of the breaking of the symmetry, where if the centroid is shifted and it creates an extrinsic orbital angular momentum. So with these three types of angular momentum, there can be interactions between them. And based off the interaction, there can be two types of interaction: spin orbit interaction and orbit orbit interaction. In spin orbit interaction, the spin interacts with extrinsic and intrinsic, creating to a concept called a spin Hall effect of light. And spin to intrinsic orbital angular momentum will generate vortex beams, that is the orbital angular momentum carrying beams. And this intrinsic OAM carrying beam can interact with extrinsic orbital angular momentum, creating the orbital Hall effect of light, which splits the topological charge to plus and minus sign. Now, due to this interaction, a specific type of phase is generated called as the geometric phase. Now, we know about the dynamical phases, which is related to the path length, but unlike the dynamical phase, geometric phase is not related to path length, but to the polarization, the change in the polarization or in the propagation vector, that is the k vector. Now, based on this change in polarization and the k vector, the geometric phase can be divided into spin redirection Bury phase and Pancharatnuri geometric phase, where spin redirection happens when you have a linear, so consider a linearly polarized state is input into a fiber, and the fiber has been twisted. So locally, the polarization is not changed, but when you have a global coordinate frame, it seems that at the output of the fiber, your polarization is rotated, but you are not changing the path length. But even though if you are not changing the path length, because of the continuous change in the k vector, your polarization is rotated. And this type of rotation, which is related to the change in the k, which is the wave vector, is called as the spin redirection Bury phase. The other type is the Pancharatnuri geometric phase, which is the continuous rotation of polarization. For example, if you have a left circularly polarized light, when passed through a half-wave plate retarder, which is oriented at beta angle, it changes to a right circularly polarized light by acquiring an extra phase of 2 beta. And here the 2 beta is generated, not dependent on the path length, but due to the change in the polarization. And this geometric phase is called as plus minus 2 beta. And this is called as Pancharatnuri geometric phase. For the work that we will be presenting, we will be only considering the Pancharatnuri geometric phase, which is due to the continuous change of the polarization. So here the Pancharatnuri geometric phase is directly related to the orientation axis of the homogeneous anisotropic medium, which is, for example, here it is the half-wave plate retarder here. Now, it's known to the community that when you have a homogeneous polarization, that means a pure linear polarization or circular polarization, when it is passed through a inhomogeneous medium, inhomogeneous in the sense its orientation axis of the medium is spatially varying, then it generates a Pancharatnuri geometric phase. So here, due to the generation of Pancharatnuri geometric phase, and since the spatial axis is spatially varying, the Pancharatnuri phase that is generated will also be spatially varying. So because of the spatially varying Pancharatnuri phase, which is related to the orientation axis, it leads to a spin splitting. That means when it is projected to a circular polarization state, which is a left and right, the beam centroid gets shifted and resulting in a spin Hall effect of light, which is known to the community. Now we thought of reversing this phenomena, that is inputting an inhomogeneous polarization, which is a space varying polarization, passing through a homogeneous medium. That means whose orientation axis is fixed, which will eventually generate Pancharatnuri geometric phase. So first we checked whether this happens, whether it generates the Pancharatnuri phase or not. So for which we have taken a radially polarized light, which was generated using a S-wave plate component, whose orientation axis is spatially varying, and is passed through a homogeneous medium, that is the quarter wave plate, and is projected to circular polarized state by rotating this analyzer medium, quarter wave plate, plus 45 and minus 45. So what we saw is that by projecting it to different polarization, we see the rotation of the loops, which actually tells you about the rotational spin Hall effect of light. That means by taking an inhomogeneous polarization passed through a homogeneous medium, also will generate a space varying Pancharatnuri phase that eventually led to the spin splitting or the spin Hall effect of light. Since the system or the input space varying polarization that we took was a symmetric case, we eventually got a rotational spin Hall effect of light. Now what we did was that we broke the symmetry. We took an inhomogeneous polarization system, which is asymmetric, which was generated using a spatial light modulator. Spatial light modulators are basically liquid crystals sandwiched between two orthogonal polarizers. So when you have a voltage given to the system in terms of the gray level values, all the liquid crystals will be perfectly aligned, and when you change the voltage value by inputting the different gray values, the orientation axis and the twist axis of the liquid crystals in between, sandwiched between the polarizer, will get changed, and eventually giving us different elliptical polarized light. So if you are creating a space varying or a gradient grayscale to the spatial light modulator, you have a spatially varying polarized light. So this spatially varying polarized light is now passed through a half wave plate, which acts as the inhomogeneous medium here, and is projected to the circular polarizer analyzer, which is a pair of quarter wave plate and polarizer. Now we want to check whether this also generates the Pancharatnuri phase. How we'll check? We again will check whether there is a shift in the centroid of the beam or not. So where the centroid shift was detected by projecting it to left and right circular polarized light, and this was the gradient that we provided onto the spatial light modulator, and there was a clear cut of spin splitting, which gave us a signature of spin Hall effect of light. Now we have spin Hall effect. So now we know that inhomogeneous polarization, when you pass through homogeneous medium, generates the Pancharatnuri phase. And we know that the Pancharatnuri phase is directly proportional to the orientation axis of the polarization. So this was the parameters that we gave to the spatial light modulator to generate this type of spatially varying polarization state. So this was the polarization axis of rotation, and the ellipticity was given, and this was the theoretical geometric phase calculated. Now, as a lab proof of concept, we would like to get back this space varying polarization by measuring with our own polarimetric system. So we will be retreating this polarized state, which is input to the spatial light modulator, for which the tool that we will be using. So in order to calculate the polarization, the full polarization information, you need to have two information. You need to calculate the polarization axis rotation or the angle of polarization and the ellipticity, that which will give you the full polarization information. Now, in order to do this, we have the tool. We have used the tool as Mach-Zehnder interferometer, where you have a spatially varying polarization state in one path, which is generated using a spatial light modulator, then pass through a half-wave plate, which will generate a spatially varying Pancharatnuri geometric phase. And the other path with a reference polarized light, which is a linearly polarized light, and is being interfered using a beam splitter and is imaged onto the CCD. Now the interference pattern will be imaged onto the CCD. And this was the basic experimental setup that we used. Now, before moving on to the actual measurement system, we'll again say the orientation axis of the polarization will give the information of the Pancharatnuri geometric phase, which is actually the difference between the total phase, that is when you have a spatially varying polarization, you have a Pancharatnuri phase as well as this dynamical phase of the interferometer. So when you subtract it from dynamical phase, you will get the Pancharatnuri geometric phase. Now, the contrast of the interference or the pattern will give you is the function of the orientation angle of the polarization and the ellipticity. So from geometric phase, you know the information on the orientation angle of the polarization, and once you know the orientation angle, if you have a calibration of the contrast plot, you'll get to know about the ellipticity, thereby getting the full information about the polarization. So yeah. So this was the calibration curve where you apply different constant gray level value to the spatial light modulator. It's not a gradient. So that will eventually give us the dynamical phase. So eventually we calculated the normalized contrast with respect to the ellipticity. So this was used as the calibration curve. Now you applied the spatially varying gradient gray value, which is this, to the spatial light modulator. And you have a spatially varying contrast interference fringe here. From interference fringe, you calculate the total phase, and without the gradient, you apply a constant gray level value to the spatial light modulator. You get the dynamical phase of the interferometer. So by taking the difference, you get the Pancharatnuri geometric phase. As I've told mentioned before, the spatial light, the geometric phase will give you the information on the angle of orientation of the polarization, and you have the contrast information from this interferent, which is the spatially varying contrast information, and from this calibration curve you get the information on the ellipticity. So this was the results that we obtained. So we using this method, we retrieved the ellipticity, both ellipticity and orientation angle. So if this was the beam and this was the cross section, so the gradient was applied along y direction. So the position along y direction was plotted in x-axis here. So at each point you have different retrieved and input orientation and elliptical value, and this was the input polarization and the retrieved spatially varying polarization. So in short, the single shot polarization measurement using the geometric phase polarimeter can be carried out by just determining the contrast, which will give us the information of the ellipticity and the orientation, and dynamical phase and Pancharatnuri geometric phase, which will give us the information on the orientation angle of the polarization. So before getting to the measurement, what you need to do is, just like any other instrument, you need to have a calibration curve. And the estimate totally depends on your interferometry, how stable your interferometry. So how stable that totally depends on the stability of the. Yeah, I'm done. So I'm nearly done. So yeah, so it depends on the interferometer that you are using. So that was the work. So with this, I acknowledge my supervisors, Professor Nirmali Ghosh and Professor Dibyendu Nandi. My research progress committee members, Professor N. Banerjee and Professor Rajesh Kumble Nayak, funding agencies MHRD and SERB, SESI and Myoptics Bionap members, and I also thank the organizers of NSS 2022 to give me this platform. With this, thank you.
That's nice proof of concept, Athira.
Thank you.
Yeah, Rana sir, do you have any comments on this?
No, I think it was pretty good proof of concept for the technology that you are working on. I just had one small kind of curiosity that let's say once this proof of concept kind of materializes, what will be the main applications for this particular technology?
Of course, the polarization measurement is what we were intended to do. So
Okay.
right now, so our Apex lab actually does the Stokes-Muller polarimetry. So we are eventually planning to replace the Stokes measurement, the traditional polarimetric measurement, to this type of measurement where you actually can save the time. So traditionally, you need to do 6 measurements to know the polarization characterization.
Correct.
Or for Muller-metrics, you need to do 16 measurement. So if you have this method, you have with one measurement, and if your system is stable enough, then you can replace this. And also as I've told in my motivation slide, this is mainly suitable for high dynamical system, such as the solar corona, where the activities are pretty fast. And so if you are using the traditional polarimetry, by the time you project to different polarization, your activity might have changed. That will lead to error in Stokes measurement, and which will actually lead to a large error in estimating the magnetic field, which will actually give us a pretty much a high uncertainty in determining as the application we intend to do space weather prediction, but eventually will get us high uncertainty values.
Okay.
So yeah, so the main motivation will be towards this high dynamical system.
High dynamic. Okay, great. Okay, thank you.
Yeah.
Thank you very much. Yeah, we'll be moving to the next presentation by Nishant Singh from PRL. Development of SDD-based large area X-ray spectrometer with ASIC readout for future planetary missions. Dr. Nishant Singh, sir, you can start your presentation.
Is my slide visible?
Yeah, it's
Hello.
visible. Yeah, it's visible.
Okay. Good evening, everyone. My name is Nishant Singh, and today I'll be talking about development of silicon drift detector based large area spectrometer with ASIC based readout aimed for future mission. So, wait a minute.
Hello.
Hello?
Is there some issue?
Hello.
Looks like there is no audio.
Nishant,
Yeah,
you're,
am I
now it's audible.
So where did you lose me?
So maybe the slide you have to start.
Okay. So the main objective of development of large area spectrometer is to develop to accurately measure the low count rate soft X-rays in energy range of 500 to 10 keV with high enough resolution. Such an instrument can help us in various applications ranging from elemental mapping of planetary surface to study of astronomical objects to X-ray imaging and so on. Low energy large area detector is also part of Daksha mission aimed at study of electromagnetic counterparts of gravitational waves. The instrument we are proposing uses multiple silicon drift detectors for X-ray detections due to its superior performance in terms of resolution and count rate. Today I'll be presenting the characterization and performance of Verdi ASIC, which is an application-specific integrated circuit used for front-end electronics for the multi-detector large area spectrometer. Okay, so the detector we are using will be silicon drift detectors. KTIC made H150 we are going to use. So KTIC has heritage in making silicon drift detectors for planetary missions. We have used KTIC which was one H30 for APXS and XSM on Chandrayaan-2 mission. The active area for the silicon drift detectors is 150 mm square. In APXS and XSM, we used SDDs with FET integrated with the silicon chip, making the first stage for amplification and FET based. But now currently we have advanced ASICs SDDs available, which come with CSP integrated with the chip. So that makes the capacitance of the detector very low, and hence gives us very high resolution. It also has integrated Peltier cooling with the detector, which allows to keep it at the required temperature for high resolution for better performance. So, the ASIC that that I'll be talking about is a Verdi ASIC. As SDD. The single channel of an SDD spectrometer will consist of SDD followed by CSPA, a shaper with baseline restorer that is given to peak detector and then given to processing electronics to extract the information of any interaction that is happening on the silicon drift detectors. For single channel, it is easier to design electronics with discrete components like we did in IPXS and XSM. But when we have multiple detectors, we're using discrete components, the device can become very large and will require very high power. For example, the single CSPA and shaper channel in APXS is around 25 mm by 80 mm, and if we want like multiple channels, the instrument becomes quite high, quite large and bulky, and it will require quite high amount of power. Hence, we are moving to ASICs, application-specific integrated circuits, that will help us to integrate multiple channels in compact size with sufficiently low power consumption. So the Verdi ASIC we are using is a multi-channel ASIC. It includes 8 channels, each one composing of a CSP, charge-sensitive preamplifier, shaping amplifier, baseline holder, and a peak stretcher, along with output buffers. So the whole 8 channels is can be like put it in. If we are seeing here, it is a 3.5 cm by 3.5 centimeter. IC that can include the whole ASIC, and the power with very low power consumption of 170 MeV megawatt. We can do the whole we can design the whole front-end electronic. So this is the basic schematic of the ASIC, with each channel consisting of CSP, a shaper, peak stretcher, and baseline holder. And along with that, we have buffers for individual channels and multiplexer if we want to select whatever output we want. We also have in the ASIC, we also have current and voltage references along with digital logics and register if we want to store the info if we want. So the Q-based, like if we are using FET-based silicon integrated silicon drift detectors, we can use the CSPA from the CSPA inside the ASIC, or if we are using a cube SDD, then we can directly give the output of the signal to the shaper. So the output of the silicon drift detector will integrate all the charges that are coming into its active area, and it will it is given to the charge sensitive amplifier, which integrates all the charges along the feedback capacitor. So the output of a CSP is in form of a ramp with small steps showing any events that are occurring, that are happening, that it is detecting. So these steps are given to shaper so that it can the steps on the ramp can be converted into semi-Gaussian signals for better signal to noise ratio, and then it is given to peak detector or peak stretcher, which will give us information about the peak height information of the signal that is incoming, and hence what is the energy of the incident radiation. In case the count rate is sufficient, like if count rates increases, what happens is the baseline starts getting offset. So we use a baseline of holder, which will bring the offset to 0 again. So all of this is combined in every channel. So like every channel will consist of these parts, and we have 8 channels that we'll be using. So currently we are using this ASIC with the board called IDA board. So it has 8 independent channels. We have 15 gain settings, which we can increase and decrease based on our requirement. We can operate our device in 8 different shaping times, and we can select our own acquisition delay and thresholds for every channel. We can even take single output from any channel we want, or we can take a multiplexed output based on our requirement. So there are various settings, various parameters that we are. The board is highly configurable. There are various settings that we can change as per our requirement, like channel settings. If we want to allow control, like how we are going to trigger our device, how we are going to set up threshold for each channel or for the whole channel. We can also have provision to manipulate how we are going to use the preamplifier. Are we going to enable it or disable it based on our requirement? Like if we have a FET based STD or Cube STD, then we can also modify the baseline holder configuration to get better sound on signal to noise ratio, and the shaper and peak stretcher in configuration can be managed, can be changed based on our requirement. Like if we want high count rate, then we can put like lower shaping time, hence enabling us to go with that higher count rates also. So first we did is we have characterized the ASIC using different type of input signals to replicate the signals that will be coming from FETs. So we have used different impulse signals and signals like for ramp signals with small steps in the range of 0.5 millivolts to 100 millivolts, but different frequencies to mirror the SDD output. And we have tried to change the parameters of ASIC like shaping time, the thresholds, gains, and dynamic range to find out how it is performing. So with the input gain of 7 between ASIC and the detector, we found that the minimum detectable step size is around 5 millivolts. So if on the ramp the incident signals are producing charges which are above 5 millivolts, we can detect them. So that corresponds to a low energy cutoff of 500 EV, and the maximum we can detect is 15 keV. So we can detect X-rays ranging from 0.5 keV to 15 keV as we required for our application. We have characterized the ASIC for different signals at different channel to find out the particular gains in individual channels. We have done the gain calibration for all the channels. We have also characterized the ASIC with different shaping time to see the improvement in resolution with increasing the shaping time that we observe. So basically 2 plots we see is, first one is how does the gain, we have done the gain calibration for individual channel, how does gain changes for every channel, and then we have done for different by changing the gain of each channel, how the peak is shifting, in spectrum how the peak channel is shifting. So here we are showing the performance of ASIC. So we have used the ASIC that we have, a Verdi ASIC, and along with the CSPA from the XSM based system that we had. So we have given the output of CSPA to the Verdi ASIC, and we have found that with different shaping times, how our devices perform. So the resolutions ranges from 180 at 5.9 keV at 4 shaping time, and it we are getting the best performance at 2 microsecond shaping time. That is 136 EV. We got the best resolution, and we have also calculated the equivalent noise charges for the different shaping times. And as we can see, as we expect that the equivalent noise charge will be the contribution from the parallel noises and the series noises. So at lower shaping time, the series noises perform, and hence and at higher peaking times, the parallel noise are dominant. So there will be a particular shaping time where we will get the best performance. So based on that is theoretically, and based on our experiment, we found that the best performance we got was at the shaping time of 2 microsecond at around 136 keV, and the electronic noise of the system at, at that shaping time was around 8 electrons, and it varies from 8 electrons, and it goes high till for the given for the shaping times we have tested, it goes till 43. So the as currently we have only tested the single channel performance. Now we are planning to incorporate the do the experiment with multiple channels and design the control of the ASIC in-house. Like currently we are using the AIDA board, which we have not designed ourselves. So the future work is to design that ourselves. And we are also working with semiconductors, SCL Chandigarh to make our own ASIC for this application, and this is at last I have put the Daksha detectors, where we can see that the low energy detector package, this is what we are planning to make. We are trying to make low energy as a large area silicon detector spectrometer with ASIC based front end electronics to reduce our hole size and get us good performance in terms of the resolution. Thank you.
Thank you very much, Nishant, for a timely presentation, and you have given very nice inputs. Any question? I have one small doubt, because when you are using almost like 8 channels, how do you be taking care of isolation among the channels? Because here you have told about only single channel, and in future, what is the plan for that, or any specification you are making for interchannel isolation? Nishant?
Am I audible? Hello?
Yeah, now you're audible. One small question to you.
Yeah, I got the question, sir.
Yeah.
So currently we have with detectors, we have only tested the single channel, but while characterizing, we have done that for multiple channels also. Like we have given same from the function generator, we have given signals to the multiple channels, and found that there is some crosstalk, but we are trying to limit that. So that is a work in progress, sir.
So currently, how much isolation you are seeing? How much crosstalk you are seeing?
So the resolution that we got, at best resolution, was around 136. That worsens to 150 EV at 5.9 kV. Sir.
Okay. So Rana sir, do you have any questions?
Hi. Go ahead, sir.
Yeah, go ahead.
So one question is, you said that you are working with SCL to develop your own ASICs for this. So has something like that been done before?
No, sir. As of now, we are just starting the process. As of now, we don't have any indigenous developed ASICs. We are planning to do it.
That would
so
be
we
great.
have had a meeting with them.
Okay.
We presented our requirements, and we are in conversation with them to develop our own ASIC.
That's a very nice development. Thanks.
Any question? Further questions from attendees, or so? If not, then we'll move to next presentation. Thank you very much, Nishan. Then next one is by Dharma Narayan Rath from ISRO.
Thank you, sir.
Indigenous 18-meter antenna at IDSN for planetary and deep space missions. Dr. Dharma Narayan Rath is available. Are you available? LOC can kindly confirm the availability of speaker.
So he's not available in the meeting right now. So we have tried to reach him, but we could not reach him.
Okay. So if not, then Rana sir will be moving to the next one. Is it okay?
Yes, that should be fine. Yeah.
So next one is by Saksham Badani from MIT University, Planetary Rover Prototype. Are you available?
Hello.
Yeah.
Yes, sir.
Yeah. Are you available?
Yes, sir.
Yeah. You can start your presentation.
Is it visible?
Not yet. Yeah. Now you can make a full screen. Yeah.
Greetings, everyone.
Yes. You can go ahead.
Greetings, everyone. I'm Saksham, and today I'll be presenting the project on planetary rover prototype, Mars Amity Surface Characterization and Operations Trainer, Mascot 1. This project was developed for conducting analog Mars missions. The system is remotely controllable, and the live video feed is relayed to the base station continuously. It has integrated sensor array for atmospheric and terrain analysis, and a navigation test was conducted during the Scientific Expedition Earth and Science Exploration Program ESCP 2021, organized by Amity Center of Excellence in Astrobiology. The objective was to develop a mobile test platform for Mars analog instrument and subsystem testing. The requirement was to develop a system that can operate in all weather and all terrain conditions. To ensure a seamless integration of new instruments and scientific payloads, the system needed to be highly modular. And lastly, the rover needed to be capable of monitoring the environmental conditions and conduct habitability investigations. So the science workflow of mission consists of deploying the rover near the area of interest. Then the rover is scouted remotely using a live video feed. The science team selects a site based on the visual and geomorphological features. And once the rover is at the target site, habitability investigation is performed using an array of sensors consisting of anemometer, total volatile organic compound sensor, non-contact IR thermal sensor, temperature, pressure, and humidity sensor. Additionally, work is in progress to integrate a stereo camera and a 2D lidar for terrain analysis and mapping. So the rover was designed to ensure modularity, and hence the frame and the rigid members and the mechanisms were made using T-slot aluminium channels. The rover has a passive suspension utilizing 3 parallel 4-bar mechanism to ensure stability of the chassis and instruments. So here is a video of motion study of the suspension. So as you can observe, the parallel 4-bar mechanism works quite effectively. The developed rover can operate for prolonged duration at temperatures below 0 degrees Celsius due to the aluminium wheels and multi-layer polymer insulation consisting of 2 polypropylene sheets sandwiched with a closed cell polyurethane foam. This is a video of basic terrain traversal testing of the rover. Navigation tests were performed on 3 different types of strata, ranging from small boulders to sand with pebbles to soft marshy terrains, terrain of the lake bed. It also had salt crystals, since Sokar Lake is a hypersaline lake. Also, in our knowledge, this is the highest altitude rover testing ever done at an altitude of 4,530 meters or 15,280 feet above sea level. So the picture on the left hand side is of the rover testing on the lake bed. while the picture on the right is of testing on rocky terrain. Interestingly enough, both of these sites are within a range of 50 meters. This brings us to the test sites. So the Soka region of Ladakh has extreme environmental conditions like cold, high UV index, low oxygen levels, etc. All these conditions combined present an excellent analog for Mars. Due to different stages of erosion, the topology varies significantly as shown in the images. Additionally, there are glaciers and hot springs which provide us with muddy and marshy terrains as well. Due to its excellent resemblance with Mars, a region as shown in the picture on the left has been finalized for development of Mars Amity Research Station, in which future Mars analog missions will be conducted. The image on the right is of sand ramps in the Sabu region of Ladakh, which is another variation of terrains in the same region, which is also similar to Mars. So now, since the Himalayan region was formed due to collision of tectonic plates, and a variety of rocks and minerals can be observed in that area. So the Indian plate, the Indian side of the Indian plates, you can observe the sedimentary type of rocks that were pushed up from the bed of the Tethys Sea, while on the Eurasian side, there are solid rocks. For the communication setup of the rover, a 5 GHz module is being used. The onboard setup is a Ubiquiti M5 transceiver being used with a 10 dBi omnidirectional antenna, while a Ubiquiti light beam M523 is being used on the base station. Theoretically, this setup can provide us a range of more than 10 kilometers, but due to line of sight issues and other losses, we have determined its range to be 5 kilometers. So further work and testing needs to be done on the system, and a prolonged deployment with extensive data collection needs to be planned. We are also planning to integrate solar panels on the system in future iterations, and a drill for sample collection will be another beneficial addition to the system. Integration of some other scientific instruments is also being planned for future missions. So I would like to thank Amity University Mumbai for support and funding of the project. I would also like to thank Chief Wildlife Warden of Ladakh for approval, and the committee of NSSS for providing a platform for presenting the work. These are the references. Thank you.
Thank you, Bhadani. Very nice model that you have shown of the rover model. And maybe the you may have to submit a proposal to the to proper channel, and you can get for your future space missions of proposing these things, and also other testing has to be carried out with all the sensors and some sample results. All the best for your future work.
Thank you, sir.
Any questions from attendees?
Yes, I have a question. Sanjay Mishra from PRL.
Yes,
sir.
Yeah, so means can you just give an elaborate on the sensors that you have incorporated that are being tested? What are all the sensors?
Okay, so we are using a anemometer, a non-contact IR thermal sensor, a temperature, pressure, humidity sensor, and a TVOC sensor.
Okay, so the means the black that rotating wheel that I can see on the top, is that the anemometer?
Yes, sir.
Okay, so means there are two designs of anemometer. There means did you explore the other designs of anemometer?
Yes, sir.
At the same? Okay.
So like due to the budget constraint as well as the current situation, we integrated the instruments that we had available.
Okay, so just one kind suggestion, that means whatever things you're designing, just keep in mind to design it keeping in with the qualification processes, since it is going to be operating on Mars, let us say. Just keep that in mind. And means I thought that this prototype, I did not know that it is not yet officially collaborated with ISRO or any such agency. So that is why I asked. So means regarding power and other things, just keep those things in mind, that how things will be operational on Mars.
Okay, sir.
Yeah, thank you.
So the battery system for this is LiFe PO4 cells. So like they can operate well below 0°C for prolonged duration and provide constant current at that temperature as well.
And design aspects of specific subsystems like wheels or electronics packages or the overall assembled rover. So
Yes,
the design process flow, maybe you can, it is better to follow the the prescribed process flow from the scratch, instead of means designing without any process flow, then later on trying to in means go with that flow. So try to get the proper design flow, the means kind of like the QA and QC requirements that are put. So try to design initially in that way, so that later on you don't have to do a lot of switching between these processes and such.
Okay, sir.
Understand? Yeah.
Yeah, today afternoon session, Dr. T.P. Das has told in a brief, a very nice talk about that payload related qualification levels and other details. Maybe and in the YouTube we can follow that video also once again and for future work.
Sure, sir.
Yeah. So any more questions, sir?
No, I think it's fine from my side.
Yeah, yeah. Sir, if no question, then we will move to the next one.
Thank you, sir.
Yeah, thank you very much, Badani. The next presentation is by Abhijit from IIT Mumbai. Development of a Compton imaging camera for space astrophysics.
Okay. Hello. Is my screen visible and am I audible?
Yeah. You can go ahead.
So, yes. Okay. Hi all, it's a pleasure to give a talk in front of you all. I am Abhijit Godgaonkar, project engineer at IIT Bombay, and on the behalf of IITB, PRL and TIFR, I would like to present this talk titled Development of Compton Imaging Camera for Space Astrophysics. So the overall outline of the talk is, first I'll be talking about the motivation about why to do Compton imaging, the laboratory setup that we have done at IIT Bombay, the electronics circuits and design that we have done, the software simulations, and finally completed and future work. So the motivation to do Compton imaging is huge. Currently the hard X-ray sky is underexplored. So the missions like Integral, SwiftBat, CZTI only scan a part of the sky at a time. So SwiftBat scans around 11% of the sky, CZTI scans 0.5% of the sky. So currently there isn't any all sky monitor at hard X-ray regions, and the proposed mission Daksha is addressing that. So if there is any astrophysical source that needs to be localized, Compton imaging is important. Compton imaging is using gamma wavelengths, but our aim with this experiment is to demonstrate Compton imaging in hard X-ray regime. That means 100 kV to a few 100 kV energy photons we want to demonstrate. And this has never been done before, so that is our motivation. Before going into the details of the project, we'll just be talking about what exactly Compton imaging is. Let us consider this simple construct. We have a radioactive source or astrophysical source. We have a set of detectors. Let's say this first detector is the scatterer, the second is the absorber. If you have a high energy incident photon on the first detector, it hits the first detector at a point, deposits some energy, or depending upon the energy of the photon, it either photoelectrically absorbs or get Compton scattered. And then it hits the second detector. On the second detector, again, a bit of energy gets deposited. We get values of the position of interaction and the energy. And from the scattered ray, we are able to back project. And the back projection makes angle theta, delta theta with the incident ray. And from the delta theta, we can trace out a solid cone. And at the all sky, it is a ring or an annulus, which gives a rough idea of where the source is. Let's consider another photon which hits the first detector at some other point and then gets reflected to the second detector. And we have the set of positions and the energy deposited on both the detectors. We get this particular back projection cone. Now, for a radioactive source, there will be thousands of counts or thousands of photons every second. So there will be a lot of back projection cones that we'll be having. So the intersection point of all these cones will be giving us the final source location. And this is basically Compton imaging in a nutshell. And this, I would like to reiterate that this hasn't been achieved in hard X-ray region, and this would be the first experimental setup for it. Now I would like to discuss about the laboratory setup. We have divided the design into 3 aspects. We have hardware, electronics, and simulations. If you see in the hardware, we have the radioactive source, which will be shining the photons onto the first detector, which is the scatterer, and then onto the second detector, which is the absorber. Both these detectors will be giving digital readouts to an FPGA, which is a device, a logic device on a board. So this device will process both the readouts and will be sending the data over to the computer. This entire hardware will be geometrically modeled using simulation softwares like Jan4 and Megalith, and we'll be able to get Compton interactions using the simulations. With both the electronics and simulations, what we try and measure are 3 things, which is the position of the photons, the time of interaction of the photons on both the detectors, and the energy of the photons. And with all these 3 information, we are able to find out source properties. So in our lab setup, we'll be able to find out where exactly the source is located. But for an unknown astrophysical source, we would be able to even find out the source spectra. So let's try and go into the details of each of these parts. First, we'll go into the hardware section. The detectors that we are using are cadmium zinc telluride detectors, or CZT for short. These detectors are used in medium energy astronomy, so they have a sensitivity of 20 to 200 keV. They have been used in past Indian missions RT2, Astrosat, Chandrayaan-1, and in the upcoming Aditya L1 mission. The expertise on this detector is at several places, so PRL, TIFR, URC, and also IITB. The detector is quite simple. It's a square of 4 by 4 centimeter, and it has a 16 by 16 grid of pixels. So there are 256 pixels, and each pixel has a width of 2.46 mm. The semiconductor wafer is 5 mm thick. So detector module, what you get is ASICs inside, and these ASICs are able to give instant parallel readouts. So that means that we will get instant parallel readouts, and this can be digitally processed. So there are some pins here which will be digitally sending off this data towards the readout system. So this is basically about the detector. Now let us talk about the setup. The setup is constructed in a modular fashion. We have a big aluminum box. This aluminum box will be shielded from the inside by lead sheets for safety reasons. We'll be having a radioactive source which will be kept at any point here. And then we'll be having a fixed scatterer detector here. And for practical reasons, we have chosen 6 absorber positions. So if you can see this 1, 2, 3, 4, 5, and 6. So we have chosen 6 positions, and this exactly construct is what we have used in our simulations. And to make a coherence, we want to also make this exact construct in the hardware setup as well. And so this basically setup will be constant throughout the experiment. Now, before moving on, I want to discuss what exactly is inside one box. So this box is nothing but the single detector box or single detector readout box. It basically has a PCB, custom PCB, on which the Orbital detector is mounted. This is a version 1 which we developed last year, so you can get low voltage supplies, high voltage supplies, and also digital readouts are sent over. Based upon the learnings of this, we improved the design and we made version 3 PCB, which had better filtering circuits and so on. If you see, the detector is mounted on the top right, and this PCB will be placed inside an ESD box. So this ESD box is light tight. So that means during the experiment, there won't be ambient photons leaking inside. And this ESD box will be mounted at any of the 6 absorber positions. Now this readout PCB is connected to an FPGA card, and I would like to discuss more about it. So the FPGA that we have used is a Zinc 7020, which is used on a PIC development board. We have used this at IITB at various projects, so we have significant expertise over it, and we have used it even for this project. So this board can interface up to with 2 detectors, and we can get readout from both the detectors. And the FPGA itself contains the processor core and the FPGA logic. So we are able to design the readout system on both of this. The readout system takes the events and time tags it. So we are trying to achieve 1 microsecond resolution in time tagging. Now this entire data is packetized and sent over to the PC interface via Ethernet. So this is basically how we are dealing in the FPGA section. Finally, we move on to the PC interface. The PC interface is made using LabVIEW. So we are able to initialize one or multiple CZT detectors. We are able to set their LEDs or enable or disable their pixels. And we are able to do on the fly, we are able to get their spectra and 3D intensity maps. So with this on-fly data, visualization of data, we are able to do a series of experiments, and it helps to streamline the experiment a lot. Now we'll talk about some early tests that we did. So we just took old CZT detector that we had, and we had a weak radioactive source, americium 241. We suspended the source just directly above the detector and tried to get the readout. As you can see, the detector was able to register counts in this specific pixels, and the spectra of this detector, as you can see, it looks like this. So we set a threshold of 40 keV. We had a long noise tail because it was done at a room temperature, but we were able to get counts in 60 keV region. So when we tried and fit this with the americium line, we were able to get energy resolution of 16%. Now this is a big milestone, considering that we were able to design the entire single CZT readout system from scratch, and it was on par with the results of the past celebrated missions like AstroSat. So this single detector board does give spectra. So that was the inference with this experiment. Now our main second part of the readout system was to do reconstruction. And reconstruction we are doing on the FPGA side. So there are two reasons to do that. So the reason is first is that the FPGA is it is a parallel device, so it is able to we are able to design faster algorithms on it. And second is it is a simulation of a payload like setup. So if you have reconstruction done in the experiment itself, it is much better. So the Python codes that were written for reconstruction on the PC side, they had a bunch of simulated photons, and from those photons we were detecting double events. And from these double events, we applied the Compton reconstruction algorithm, and we got localization in about 30 seconds. Now the same algorithm, if we try it on the FPGA, we were able to process 250 double events in 2.3 seconds, which is an order of magnitude faster than the PC. And if you see, this is the localization plot of the FPGA reconstruction. You'll see that there is a hotspot form here of all these double events, and this is between theta and phi. So if you just see, the source is located exactly where at theta is equal to 0 and phi is equal to 60 degrees. So FPGA reconstruction was possible with moving on to the simulations, we have used the popular software JANT4, which is used across all domains in physics. On top of that, we have used Megalib, which is a gamma ray astronomy library. And with this, we have done simulations at various photon rates and energy rates. So we took energy rates of energy levels of 122 keV, 200 keV, 356 keV. I'll be showing a key result, which is of barium 133 at 356 keV. With this, we were able to do the entire Compton setup, Compton imaging and reconstruction. So if you just see, this is the box that we discussed a few slides earlier. There are 6 absorbers and 1 scatterer and the radioactive source. So if you just take absorber 2 as active and the scatterer and the radioactive source, we are able to get a plot, localization plot, which is just a projection on the sky. So we aren't able to determine where exactly the source is. But if we take 2 observers, what we are able to do is we are getting 2 rings, 2 annulus, and the intersection of them gives a hotspot. And if you see this dashed line and this dotted line, these are nothing but the injected source position and the recovered source position. And this is roughly an overlap over the hotspot. Now, if we try and include all the absorbers, we get only marginal improvement in the localization. So our inference with this experiment was Compton imaging is possible using this setup, and the ideal setup would be to have 2 observers. So that was the inference from this setup. Finally, I would like to discuss the overall progress that we made. So in each front, we made a progress. So first of all, in the single detector readout, we were able to establish FPGA communication. We were able to procure the detectors, get readouts from them, and get a radioactive spectra. And in the back projection, we were able to design a back projection algorithm that was PC free. in simulations, we got a lot of insights which will help us fine tune and improve our setup or improve the overall experimental goal. So our future aim right now is to do 2 detector readout and to mechanically construct the aluminum box and match the simulated results with the real hardware results. So that would complete the end-to-end demonstration, and yeah, that would complete the experiment. So I would like to acknowledge several bodies. So for funding, we had ISRO Space Technologies Cell at IITB who helped us in funding, and in guidance and expertise and support, we had various labs. So Vadhwani Lab at IITB, PRL, and TIFR who helped us out during the project over the span of 2 years. Finally, I would like to thank each and every one of the members who were part of the project. So there is me, Abhijit Godgaonkar, there is Sudhanshu Nimbalkar, Sanjay Narang, Pranav Page, Amit Shetty, Rishikesh Belatikar, Dr. Saurav Palit, Aditi Marathe, Sandeep Vishwakarma, Dr. Varun Bhaleraus, Dr. Siddharth Tallu, Dr. Sriyash Tendulkar, and Dr. Santosh Vadavale, who were part of this project. With this, I would end my talk, and I'm happy to take any questions if there are any.
Very interesting talk, Abhijit. So
Yes.
here 2 clarifications I have. Basically 6 detectors you have used it.
Yes.
Usually 6 is, I mean, any specific reason, usually some 5 detectors if you keep it in a geometrical way for both directions. Basically you have to identify the location of that radioactive source, right? So,
yes.
So any specific reason of using 6 detectors, usually for any interferometric use or something. So if in both directions, if you can use 5 detectors, maybe maximum, you can unambiguously can say the direction of this one source. So can you any specific reason for this?
So we have just chosen nominally 6 locations while we were doing simulations. Also, when we are trying to procure the setup, like we chose that we will go with the number 6. So there are 6 observer locations, but we won't be using all of them at once. So at a time, only 2 or 3 observers will be used. But these locations are fixed. So we have, it's a design choice that we have taken 6 observer locations.
And one more thing is you have used Zinc 7020, that is the industrial or commercial component. But in the future, as in the morning we might have attended. So yes. When you're I mean, your for future space missions and those things, maybe the part whatever you have to use it, maybe you have to use as per the qualification levels. You may have to. This may not be possible to use it. So that you might explore, because this is a commercial or industrial grade, that is zinc based 7020 with a dual core, right? This is?
Yes, the processor has dual core and the FPGA logic has 1.3 gates, 1.3 million gates. This is not space grade, so this PCB isn't space grade.
Yeah,
That's correct.
Because now your all your processing is based on this one, so the additional capabilities you are using, maybe the actual one when you are using, maybe the processing may not be that much faster like this component. That also you can you have to keep in mind when you go for space-based model.
True.
Yeah. So that is one more doubt I have. So that much only. Any other questions are there? Let me see from chat box. Something is there. Yeah. Any questions from the other attendees? And Rana sir?
No, I think it was very interesting talk with very exciting work. And as you mentioned, like the hard X-ray area is kind of unexplored in this region. So it will be very exciting to see. And when you actually demonstrate above 100 or 200 keV, how the technique performs, that will be very exciting to see. So good luck with your future project.
Yes, thank you, Vikram sir.
Thank you. All the best, Abhijit. Very nice talk.
Yes.
So yeah. So I think we have come to the end of the session, but on the final call, we'll give one more chance to Dr. Dharmendra Narayan Rath from ISRO. Sir, if you are available, you can present. You can kindly confirm your availability. LOC, once again, kindly confirm whether he has joined the meeting.
So we did not see his name in the attendee list. So I think he has not joined.
Yeah. So in that case, Rana sir, then formally we can conclude the session.
Yes, I think, yeah, that's true.
Yeah,
Okay.
you can add some remarks, sir. Then finally I will conclude. You can add your remarks.
I think in general it was a very exciting and interesting session where all the speakers provided very nice some proof of the concept, some niche technologies that has been developed, and it will be very useful for the future space-based projects, especially in astronomy and other areas. So I think I would like to thank all the speakers for such a nice and interesting talks. And of course, all the speakers actually stick to their time. So I would like to appreciate that also. So over to you, Mr. Raghuram.
Yeah. Yes, sir. Nicely told. Conclude session. Yeah.
Yes.
I'm happy to say that all our presenters very nicely they stick to their time and they could be able to complete it within time. And very interesting talks are there. And all the best for all the speakers for their future works for upcoming missions. So with this, I think we have come to the end of this day 2. And hopefully again tomorrow we'll meet in day 3 afternoon session. Thank you very much to all. Thank you very much, LOC.
Thank you. Thank you all. We'll meet again tomorrow.
Dr. Durgarao, I think.
Yes, sir.
For tomorrow, I just saw your email for that some brief CE, right, from